Hello, everyone. Today we're going to talk about SRS shock. We're assuming that everyone has a basic background in SRS, and the intention here is to go into details into the software setup and all the bells, whistles, knobs, and switches you can flip to set up a shock test with SRS. So I already have the channel table set up. We have other webinars that go into more detail about that. This is kind of universal. The thing to keep in mind here is with a single axis shock test, there is one control channel allowed. And the reason behind that is shock can be controlled in the time domain. So with a time domain based control, how do you average together time data? It's really not a simple question to answer. So with single shaker, we have one control channel. If you're doing multi-shaker shock, you're going to have control channel that is related to each drive. So that's that error message here. So I'm just going to switch this to measure here. And we're going to go to shock setup. You can see switching that to measure, the status message went away. And we can go right in here. Channel parameters up here. This is where you would set up limiting and per channel aborts. For instance, if you wanted to abort on a peak in the time domain per channel, any channel, you can set that up here. I'm not going to go into too much detail about that. Source parameters is similar to setting up sine or random. You have an output going from output 1, and that goes into your amplifier to drive the shaker. This gets more complicated if you're doing multi-shaker type of tests, but we're not going to go into that. We're going to focus on single shaker SRS here. The first thing here is you start on the right-hand side of the screen, and we start with our control mode and reference. So the first thing is I'm going to pick SRS, and now we can see I've switched to my SRS reference setup down here. And control mode, there's a couple options. There's this inverse model, which is a frequency domain control method using an inverse transfer function. There is an iterative method, which works in the time domain. I'm going to pick iterative for this. And basically, that's a coherence-based error in the time domain, correcting those drives based on the previous drive that went out. Min and max frequency. Today, we're going to do 10 hertz to, let's say, 2500 or something like that. This would be the control frequencies. You can also synthesize a pulse in a different frequency range and have your control in a different frequency range. For instance, if you have a pulse that you're starting at 100 hertz, but maybe you want to control some of the lower frequencies too. Let's say you have some kind of noise or something like that you're dealing with, or fixture stuff, you can control in a different frequency range. Based on all this stuff, this frequency resolution, block size, and sample rate are calculated for you. Now, in the control advanced settings, there's a couple things to point out. You have this averages per loop, and that's really for your ITF, frequency domain-based control. Last equalization level is going to be where the software stops equalizing. So you might have a situation where you have a nonlinear structure, and you don't want the software to change anything about the drive once it gets past 3 dB. Or maybe you go up to -1 dB and you say, okay, so at -1 dB, we'll do an equalization, and then we'll go up to 0 dB and do pulses without changing anything. What can happen with nonlinear type structures is when you try to correct, you could end up with divergence from a stable control solution. So that's helpful with some things. That's also why we have this option for replay. And what replay does for you is if you run one of these control modes on, let's say, a mass model, you don't want to cycle your test article, you can then use replay and that's going to play out the shock pulses from a previous run without modifying the drive at all. So that's useful, for instance, spacecraft testing, where you have an SRS type pyro shock test on maybe a subcomponent or something like that, but you don't want to fiddle around too much with the real test article. So you put a dummy test article on there, you'll do your equalization with your shaker and everything, and then you'll put your real test article on and use this replay mode. But iterative combined with this last equalization level can do something similar. Coherence threshold has to do with the inverse control model, which is updating based on coherence. You can put a threshold in here so that anything that is below the threshold doesn't update. And that's, again, dealing with nonlinearities and stuff like that. Oversampling factor, you can oversample your time domain data, and sometimes that's necessary, especially when you get a situation like this. You have a max frequency of 2500, sample rate of 6400. This is probably inadequate to capture the peaks in the shock at this frequency. Generally, we like to say 10 times oversampling for shock, because if you have 10 samples of your highest frequency of interest, or 10 samples in any sine wave, you're going to miss the peak by less than 18 degrees. And the cosine of 18 degrees is 0.95, which means that you have 95% amplitude accuracy if you use 10 times oversampling. So in here, I'm going to add this oversampling factor. And if I hit apply, you can see how that changes my sample rate over here. There is a zero padding options here, and this is going to allow your shock some room at the beginning of the pulse before it starts sending information out. It's pretty good to have this. You don't necessarily want to start your shock pulse right at zero, because you might want to see what's happening leading up to the start of that pulse or something like that. That's what the zero padding does for you. Pulses per acquisition is a way to increase your frequency of pulses. So for instance, if you're doing SRS shock for gunfire and you want to get pulses out, maybe you want to do 5 or 10 pulses really, really quick in succession. The pulses per acquisition, what that does is the first pulse that gets sent out, there's a calculation that's done and the drive is updated, and then the drive is not updated for the remaining number of pulses in that acquisition set. That's what that's doing. You're basically sacrificing your drive correction to get more pulses out faster, because you're eliminating that calculation step between pulses. Static bandwidth is if you have any channels set for static acquisition. So if I go back to my channel setup, you can see here, I can actually set a static channel if I want to do thermocouples or static type strain measurements, where you might want to have something that's sampling pretty slow. Again, a thermocouple is a good example. Temperature is not going to change dynamically. So you might set a thermocouple channel to static, and then you're able to set that static bandwidth here. And then last in this advanced tab, we have this limiting scale down level. What this is saying is if I have limit channels, I'm going to scale them down to a certain point or not. You might want to set this, for instance, to 0 dB, and then your limit channels aren't going to scale down. Your limit channels are always going to be at the 0 dB level. So anything that happens that exceeds your limit profiles, if they had been scaled down, is basically ignored. Since we're not using any limiting here, it's not really relevant to this test. I'll leave that alone. So hit OK. All right, we have safety here. You have alarm and abort points. Now, keep in mind, basically, this is for the calculated SRS profile. All our alarms and aborts are based on the calculated SRS. You can set this so that let's say maybe I have 1 or 2 lines that are out of tolerance, but that's going to be okay because of some dynamics. Maybe I'll set this to a 1% out of tolerance, or 2%, something like that. Now keep in mind, we're looking at a number of lines here is based on this block size. So 1% is insignificant compared to the number of lines that we have. Well, I guess that's an opinion. Some people want it to just say, okay, 0, and that's that, right? Everything has to be within our limit lines. But this is a nice feature to be able to open that up a little bit and let the controller try to bring in those points. And max repetitive aborts is also along those same lines. This is going to say how many subsequent blocks are allowed for our limits to be out of tolerance before it actually aborts the test. Right? And you can turn that on and off. In Safety Advanced here, there's a couple things to note. You have your line aborts enablement, and this is again similar to my limiting scale down here. This is basically saying when I'm going to turn on aborts. In this case, by default, I'm starting up at -9 dB, and I've got 3 steps to go. So this will go -9, -6, -3. Those are my 3 steps. We'll do 10 pulses each one of those, and then step up to 0 dB and do 10 pulses. Having this at -3 allows that -9 and -6 level to equalize and allow it to do what it's going to do to account for dynamics and allow the control loop to learn what's going on before it starts applying abort scenarios to your test when it gets to higher, more dangerous levels. The counter to that is that we're also going to have these peak aborts enabled at lower levels. So again, your time domain aborts are going to be active, even though my line aborts may not be, if that makes sense. For an example, I might set a time domain peak for 20 Gs or something like that, and that's always going to be active if this box is checked. But if my SRS isn't exceeded, then it's not going to abort here based on the line-by-line aborts. These are all overload actions. I think they're pretty self-explanatory. If a channel overloads, what do you want the controller to do? And then the drive update ratio is how much the controller is allowed to change the drive between control loops. You have these low point aborts and shutdown times. That's just how long the controller is going to take to ramp down if there's an abort or at the end of the test, because you don't necessarily want to stop excitation right away. You end up with a transient sometimes. And then you have these minimum system coherence and max ITF ratios. That's all about your self-check stuff. It's not going to allow you to proceed or give you a warning if you have coherence below 0.5. And also if you have the ratio between your peaks and your valleys. That's what this is. If the ratio between your peaks and valleys exceeds 1,000, it's also going to give you a warning there. Schedule. This is the easy schedule setup. We've explained through that a little bit. If you want to have something a little more complicated, you can turn on this advanced table, and that's going to let you schedule, let's say, for instance, if I want to have 30 pulses at -9, 15 pulses at -6, and 10 pulses at -3, I can do that with the advanced setup. You can also set up level by level measurements and some other more advanced things here. Most of these have to do with individual level measurements. So for instance, if I do a pause, that's going to enable this. Now let me drag this out a little bit. That's enabling this column here, pause time. If I turn on the measurement, you see that enables these other columns. Do loops and end loops is gonna enable my repetition time here. And if I want to do something like run an executable, I can put that executable path in here. For instance, a good example of this is if I have a chamber that my shaker's in and I'm doing temperature cycling, I might want to use my controller to execute a change in temperature profile after doing so many pulses at a particular level. I'm going to change this all back to none here. And I'm just going to use the regular setup. And down here, the level startup mode, this is basically saying, do I want to send repetitive pulses, or I can set this to single shot. And that basically turns the controller into manual mode where I have to click a button every time I send a pulse out, which sometimes isn't a bad idea. All right. Automatic measurements, I'm not going to go into that too much. We have an article online that really goes through all this. There's your advanced parameters here, whether I want my measurements to be linear, aka stable, or exponentially weighted, and the number of averages when I hit manual mode. Doesn't necessarily make sense in this shock mode, but those are available. Online SRS calculates SRS based on the parameters that I have here on my measurement channels. And I can choose to use my reference pulse SRS settings, or I can set this independently if I want to have different SRS calculations for my measurement channels versus what's going on with my control. I'll also point out here, if you have other requirements for SRS, generally speaking, SRS is implicit that you're doing a maxi-max SRS, which is an absolute maximum of the response of this fictional array of single degree of freedom systems that we're passing this time domain pulse through to calculate our SRS. But you also have positive and negative primary and residual and maximum pulses. So there's actually 9 different types of SRS spectra. Most of the time, we're talking about this absolute maximum, aka maxi-max. But if you want to look at the other ones, you can turn that on there. All right, now we're going to go through synthesizing an SRS pulse. Now, I am going to do a pulse within the same frequency range of control. And I'm just picking numbers out of thin air here. Now, Mill Standard 810 recommends 12 points per octave and a Q factor of 10. So I'm going to keep that like that. Again, what do you want to control on? Absolute acceleration is most typical, but you have other options here. You can do relative displacement, relative velocity, pseudo velocity, and your equivalent static acceleration as well. Once I have these parameters set here, I can go into my profile editor and I'm going to set some type of frequency thing. So here I'm going to go 10 and I'm going to go out to 2500 and let's say 1G and let's say 25 Gs here, and I'll put some kind of knee frequency at 100. That looks like a typical kind of SRS pulse, right? You have some slope at a particular knee frequency, and then you have this flat line out here. Sometimes you'll also see ones that dip down at the end because higher frequencies we don't really want to excite, we just want to measure. So there's things like that. Once we have that profile set, you can hit OK. Upper and lower tolerances, you can also define this with slopes. So for instance, if I want to delete this breakpoint, I could put a left slope here. Let's say, I don't know, 6 dB, and it does the same thing. This isn't quite going down to 1, so maybe I want this to be 7. That gets pretty close, maybe 7.5. You can also set up your SRS that way. But I'm just going to go back to what I had before with the individual breakpoints. I can scale here, and down here I can also import and export from predefined profiles. So for instance, if I wanted to export this, it'll save it as this TSP file. If I wanted to load that into another test, I can pull that back in. Select block is if you have a block already set, you can pull that in from another LMS test file. So that's the profile editor. Next, we'll move into time synthesis. And this is where SRS usually gets pretty crazy. First thing to choose here is what type of wavelet am I going to use? There's 4 options here. You can pick wavelet, 2 kinds of damp sine, and chirp. Now, the difference between the 2 damped sines is the compensation used for velocity and displacement. I happen to like this envelope, which is sometimes also called a Zerd compensation. Because I have my low frequency here, I'm gonna set the duration to a second, as otherwise the controller's gonna have umbrage with that lower frequency not fitting within the window here. Once I have these set, I can go in my profile editor, and this is my time synthesis. I've got some parameters up here, and I've got some advanced parameters in here, but I'm just going to start with hitting default. Okay, and that puts some wavelets in here at different frequencies. And I can also hit iterate, and I'm looking at my error graphs here. It was pretty good to start with. And I can see my error improving here as I go along. But you reach a certain point where you see you start to get to a point where you get divergence. Nice thing here is I can go back. So let's see, this has a time domain acceleration max of -4 Gs, max displacement of 0.56 millimeters. If I go back to my other function here that has less error, it's about the same. So I'll just pick this to work with. There's some other things to fiddle with as well. Let's say I want to come in and maybe randomize my delays. That'll give me a very different looking SRS here. So I'm going to stick with this. Maybe we'll go with, I don't know, 30%. And I'll do maybe 5 iterations. All right. What this is going to do is in my profile here, I'm going to start to randomize these delays. I can hit this randomize button, and you can see what this is doing to the pulse. You can see how different it looks with these randomized delays. So you can really use this, this function to randomize delays to affect how your SRS pulse looks. So for instance, if I widen this out at 60%, and I hit randomize, all right, you see how it spreads out that energy. You can use that to modify how your pulse is looking. And again, if I want to go back at some point to a previous pulse, and just click here. But this is starting to look more pyroshocky to me than this one was without the randomized delays. That's some things to think about when you're setting this up. Another thing here to look at is this under test avoidance factor. And we'll zoom in here and see what that does. Okay, so what the under test avoidance factor does is you can see in here my synthesized SRS pulse is dipping below my reference here. And some test specifications don't allow that. The calculated synthesized pulse has to have an SRS that's 100% above the reference line. What I'm going to do here is I'm about 127 to 190. So I'll take these lines here. Here's 199. Maybe I'll go up to this wavelet here. So I'll select these and I'm going to increase that UAF. Okay. And now you can see this is starting to go up. So where is this here? Let's see. Cursor here, that's around 150. All right. So I'm going to increase this one again here. All right, and that's even still a little low. There we go. So now in that area, I've got this part of the curve that's now above my reference. So we'll go back. That's what your under test avoidance factor does. And the other neat thing is you can modify this UAF live during the test as well. So if you have something during the test that doesn't seem to be getting to the levels you want, you can do that live. So I'm going to hit OK. And that's going to be the pulse I'm going to use. All right, I've got my reference. I've got my time pulse. And now there's this initial drives as well. I don't have a model now until I do system identification. Here's my system identification screen. Again, some other softwares call this self-check. We used to call it self-check, but we now have system identification, system verification. This is a more advanced self-check process. One of the things that I'm going to do here to start with is I'm going to go into settings here, and you can see I've got this frequency resolution of 0.39. Which means my self-check is going to take a little bit of time. So I'm going to bump this up. I'm going to get less of a frequency resolution, but I'm going to make my self-check go faster. So let's see how that works. All right. Well, what do I have here? It's yelling at me about something. Pulse repetition rate is too high. All right. Good. Now my start button is sensitive and active, and I'm going to start sending out some excitation here. And there you go. All right, so now I'm going to go to system verification, and I can take a look at my coherences, see if they look decent, and they do. It's pretty good. Of course, my response channel has lousy coherences. One might expect. And I can check other things down here. I can have all my response values forward predicted to full level, and that's within the range of all my sensors and everything. I can look at my response predictions too and see if anything looks too crazy. Yeah, so that looks pretty reasonable. So I'm going to hit ARM here. A couple things here. I have my control. I have my responses, so I can take a look at my response, for instance, in time or SRS. I can be looking at this in time or SRS. So I'll take a look at this in SRS and see how that's going. I'll hit start here and see what happens. Now that is very strange sounding on my end. But you can see how the controller works. So now I can go into this manual control, and this is where I can apply these scaling factors manually. So output 1, I can, let's see here, maybe in this frequency range here, I want to go down. So what is that? Double cursor. And where am I here? So 150 to 200, let's say. 150, 200. Maybe I'll scale that down. Okay. Now I can send this out, and you can see how that's been reduced. Other things here, I can skip levels by hitting next. So right now I just go right to -3 dB. And of course I'm hitting an abort here, which makes sense. But yeah, that's pretty much SRS shock control from setting up to running the test. At this point, I'm going to say to everyone, thank you for joining us today for this webinar, and hope to see you at the next one. Have a great day.